In the next few lectures, I will be explaining 4 papers that are really interesting, and they use the techniques of integer linear programming and also belief propagation, factor graphs, and so on. So it all started by this beautiful article, Dependency Parsing by Belief Propagation, by David Smith and Jason Eisner, that all of you are familiar with them. And there are 2 related articles as well, and I will explain both of them in future. And so what is the idea of this article in 28? We formulate dependency parsing as a graphical model with the novel ingredient of global constraints. We show how to apply loopy belief propagation, a simple and effective tool for approximate learning and inference. So as a parsing algorithm, belief propagation is both asymptotically and empirically efficient. Even with the second-order features or latent variables, which would make exact parsing considerably slower or NP hard, belief propagation needs only order of n cubed time with a small constant factor. So it is good for higher order features because ordinary algorithms are good for just first order features and are just good for projective parsing. Projective, so that, for example, at the inference time you use the simple Eisner algorithm, which is similar to CKY, and everything is fine. But if it is non-projective, or if you want to have more accurate dependency parsers, you should go beyond just the edge level. You should go to multiple edges. And then that's the idea of high order features. You are implicitly creating high order features. And in as much as the first order parser finds that edge is probable, the higher order features will kick in and discourage other edges to the extent that they prefer not to coexist with that edge. And we use belief propagation, but a global constraint needs to enforce the parse tree. And that global constraint is the most difficult part of this lecture and the next 3 lectures, because we call them hard constraint. We want to prove in this constraint that it is a tree. It is not an ordinary graph that has lots of loops, and it doesn't have any loop, and it is a tree. So the observed and hidden variables, we have a sentence, W0, Wn, and so W0 is always your root. And the tags, the variables, you should obtain them as well, either jointly or separately, the part of speech. And also you have some links. For example, this is some word that is your head, and this goes to the dependent or people call modifier. So this is your head and this is your modifier. So we don't know if it is what kind of label it has. So we want to obtain these links. So if it is, for example, for unlabeled dependency parsing, if it is 1, it is an edge. If it is 0, there is no edge. And for labeled dependency parsing, we say that this value of this edge has lots of could have lots of discrete values. For example, 1, 0, 2 to m. So it can have m discrete values. We don't know which one it is. So the map assignment, if you're familiar with that in graphical models, the map assignment that is just obtaining, just assigning some values to the nodes, of any graph or factor graph, the variable nodes, then we are done, and the dependency parsing is, we can see it as an optimal assignment. So we just multiply, in Markov random field, you just multiply the factors. For example, we have m factors. So a factor function may depend freely on observed variables. For example, if, one factor could depend on this edge. Another factor is depend on another edge. So you can obtain the factors easily. So when it fires, it is one. When it is not, so that is a kind of another kind of factor which is called hard factor. For example, we want to make sure it's a kind of constraint. We want to make sure that it is a tree. It doesn't have any loop. So for that reason, we just need, it requires exactly any of these variables to be true. And that corresponds links from directed tree rooted at position 0. For example, from going from I to J. And so this tree constraints, so it's a constraint, a factor, goes to multiple nodes, multiple variable nodes, and it makes sure that it is just a tree. And so a soft factor acts as a soft constraint that prefers some parsers to the others. By now, you have seen this 100 times that we use log linear models in machine learning and NLP and parsing, for example, classical dependency parsing. And theta is the parameter that you should learn. We should learn, the machine should learn. And f is a corresponding collection of feature functions. Classically, we work on edge features. First order dependency parsers. But if you go to higher orders or secondary or third order dependency parsers, you go to 2 edges or 3 edges or multiple edges at the same time for evaluating these features. A family of unary soft factors that judge the links in a parse individually. So link fires if it is that edge is true. So I've explained this. And a first order parsing model contains only link factors because it only concerns the edges, not multiple edges. Along with the global, as I said, this is a hard factor. The hardest part of this algorithm is evaluating that it is a tree. We'll consider various high-order soft factors. For example, pair. The binary fires with some values if Lij and Lkl are both true. And there are other high-order soft parts such as grandparents or siblings, because you need multiple edges, child sequence, no cross, tag link, and trigrams. And the grand, for example, is like this. For example, we have a proposition, an object, and modifier if all of them. So this is more than one edge. So we want to make sure that, so it's a kind of higher order soft factor. And so it's a factor graph. We have some variable nodes like this, and we have some factors like this, which are constraints. And as I said, this is the most difficult part of constraint, which is tree, to make sure that it is a tree. And finally, we do believe propagation to obtain these probabilities, and the message from variable to factor. These are classic things in belief propagation, a message from factor to variable. And finally, after convergence, we compute the beliefs. Now we have all the things that we need. We compute the beliefs, and that's it.